In this video I'm providing some examples for sketching tangent and cotangent graphs, and I'm basically going to touch upon a central premise of both of these graphs right off the bat here, which is we know our ratio identities, which are the tangent of an angle is equal to the sine of that angle over the cosine of that angle. Likewise, the cotangent of an angle is equal to the cosine over the sine, since that's the reciprocal of tangent. But basically what this means is for our graph of tangent here, whenever our cosine value is equal to 0, we're going to get an undefined spot on our graph. And so let's recall from our unit circle just really quickly here. A unit circle is a circle with a radius of 1, okay? And it's always good to know these four angles at the very least. It helps you navigate to a certain extent on your graphs. But we say this is the point 1, 0, this is the point 0, 1, this is the point negative 1, 0, and this is the point 0, negative 1. And so basically these are telling us the cosine and the sine values of our angles, at least at those four quadrantal angles. So we say, where would cosine have a value of 0 at? Like what x or what input values? Let's say angles. And I say, well, cosine would have a value of 0 here and would have a value of 0 here. So basically we could say, well, pi halves radians and 3 pi halves radians. I'm actually going to change it to say negative pi halves to pi halves. And the only reason I say that is because when we graph this, instead of going from, say, pi halves, which would be about right here, out to 3 pi halves to get to an asymptote, you know, we say here are two asymptotes. We say from negative pi halves to pi halves because negative pi halves is on this side of 0 on the x-axis, and we just get this central like region on the graph. Okay, so we say that would be undefined at pi halves and negative pi halves, whereas if I look at this, we say this is going to be undefined wherever sine is equal to 0, and sine is equal to 0 here at 0 radians, and it's also equal to 0 over here at pi radians right there. Okay, so here's our method when graphing these. What we're going to do is we're going to say when we graph something that is tangent of x, we're going to set the x values, that's the stuff on the inside of this angle here. We know that if whatever's in there is equal to negative or positive pi halves, it's going to be undefined. Let me get this out of the way, actually. Try to scrape this in there a little bit. Oh man, I keep drawing over that. I don't want to draw over this down here because my next stop is this. We're going to set whatever is equal or to our angle in here equal to 0 and pi when we do a cotangent graph. So let's go ahead and talk about this right here. It says for these equations, let's graph two consecutive asymptotes for each of the following tangent and cotangent graphs. Then we're going to graph one complete cycle of the graph. Once we're done sketching one complete cycle, we're going to double that. Okay, so let's take a look at this. First few things we want to identify. We say, well, first of all, our a value is 2. Our b value, which is this coefficient of x in here, we say that's equal to 1. And then we say our d value, which I notice this has no d value out here, but I can write plus 0. So it has none. So the first thing we want to do is find the equation of the asymptotes. And the way we're going to do this is, since it's a tangent graph, we're going to take what's in here, which is just x, and we're going to set it equal to negative and positive pi halves. So we get x is the angle in there. We set it equal to negative pi halves. And then we say x, which is what is in there, that angle. We set it equal to pi halves. We say, we'll solve for x. Well, these are already solved for. So we say x equals negative pi halves. This is one of our asymptotes. And then positive pi halves is the other asymptote. Okay. So domain and range we'll talk about when we're done graphing this, but for right now I'm just going to put on negative pi halves, which I know has to be just as far to the left of 0 as positive pi halves has to be, so I can conceive of it looking this way. And so we'd say, okay, well, here are two consecutive asymptotes. From here on out, this is pretty easy. Just like any interval, we say here's the beginning, here's the end. We're going to split this in half and split the halves in half. I almost got ahead of myself. We label the halfway point as 0 in this case, but we say between two consecutive asymptotes, we know that these tangent and cotangent graphs are at a height of 0. So the only other thing we need to recognize is this. Essentially, looking at this graph here, we'd say our a value was positive. So a being positive basically means that it's not going to be reflected, about the x-axis. Okay, it's not going to flip upside down. So we need to know this because we know that tangent is usually always increasing. And the only reason I say this, okay, let me try to write this word here, it's always increasing, is because at these 2 points right here, a fourth of the way through its cycle and a 3/4 of the way through its cycle, it's going to adopt this a value as if it has an amplitude. It has no amplitude, so we can say amplitude, none. The reason why is because it never stops going up, it never stops going down, but we would say if it's always increasing and it goes through, with an a value of 2, we say this is negative 2 and this is 2, then at this first quarter mark, it must have been down here. And then at the 3/4 mark, it must have been up at the positive 2, because we have to satisfy that this goes through these points and is always increasing if it hasn't been reflected. So part of this exercise was I wanted to go out another interval length. And I want you to notice this. I have to know how far was it from asymptote to asymptote. We went pi halves to the left and pi halves to the right, that's 2 total pi halves. So we have to go out on another 2 pi halves. So we'd say 1 pi half, 2 pi halves, which is pi, 3 pi halves, which would be right out here. We could drop in another asymptote. We say it's at the ground level, cut these into fourths. We say it's down here at -2, up here at +2. Here's another section of our graph. So really quickly, let's go ahead and bury this last one here. We say the a value is equal to 1/2. The b value is equal to pi. The d value is equal to, we have no d values. We're going to say 0, so no vertical translation, that's fine. We want to find the equations of the asymptotes for this graph. So since it is cotangent, looking up here we say, we're going to use 0 and pi. We are going to set what is in there, which is pi x equal to 0. We're going to set that pi x equal to pi because if either of these were equal to 0 pi, it'd be undefined. So we're going to solve both of these for x, which means in this first one we have to divide both sides by pi. And we get x equals 0, so that's one equation of one asymptote at x equals 0. And we divide both sides over here by pi. This is kind of a fun graph because you see what we get here is something divided by itself is 1. So we have another asymptote at actually a whole number. We don't have to deal with like pi and 2 pi this time. So we say, well, here's 1. Whoops, you start writing pi. We say, here's 1. This must be 1/2. And so we'll split these up here. We had asymptotes at 0 and 1. So here's one set of asymptotes. Between these has got to be at the ground level. I notice my a value is 1/2. So it doesn't have amplitude, but I'll go, let's say up 1 and down 1 because I want to fit 1/2 in here. But here's my -1/2, here's my +1/2. We say that this is a cotangent graph. A is positive, so it's not reflected. And so since it's not reflected, then we could say cotangent graphs are always decreasing, always decreasing. So this means at a quarter of the way through its interval, it's going to be up here at 1/2, and 3/4 of the way through its interval, it must have been down here at -1/2, and we get a graph that looks like this. Okay, so I would have to go like left 1 now. We say this is left -1/2. Boom, boom. We could drop in another asymptote. We say it's at the ground level here. You see how it all just kind of falls into place now. You can just copy it out. Okay. So the thing we want to do before we move on through this video is this: basically assess domain and range. And you notice I left it for last. And there's a reason why I do this is because domain, we're just going to pick one undefined x value, like right here at -pi/2. I'm going to say that x is not allowed to be -pi/2. And this is the only one I have to name because all I have to do now is say, well, what is the length from asymptote to asymptote here? What was the period of this graph? And so we say the period would be technically equal to its normal period, which for tangent is pi, divided by b, and b here was 1, so we get pi. Or I could have just counted pi halves plus another pi halves is pi. So we're going to say plus pi times some whole number. What we're really saying is this: -pi/2 is the first place we said it's undefined at, and then we're going to take steps of length pi to the right and left of this, and always land at another asymptote, okay? And then the range is all reals. As a matter of fact, save yourself the trouble over here on cotangent. We're going to write all reals. Look at the graphs. They go up and down forever and ever. In the domain here, this would be easy. We could say 0, x equals 0. That'd be bad. So we say x can't be 0. And the length from here out to here was a length of 1 unit. So we could just say plus 1 times k, where k is some whole number. You would get all the rest of the asymptotes, so we wouldn't walk there. Cheers.